So what we looked at last time was probably problematic. I'm trying to decide if I should close the door. Maybe we wait 2 minutes to close the door. Okay, so they automatically do it. It's okay. Don't worry. So let's start with. So this was the idea behind the proof. Were you there last time? Or you not there? Poor thing. I don't know how much you'll follow. Did you? Oh, I didn't. Yeah. Okay. I mean, the lecture is on the OneDrive thing, but it's not on. I didn't put it on YouTube yet. But okay. Okay, so let me remind you what we were doing. So we were trying to argue. So do you remember anything about coset states? You didn't attend the last lecture. I think we introduced it in the last lecture. Okay, so it's not difficult. Okay, so we'll do a quick reminder then. Let's do that first. Okay, so a coset state is basically specified by a subspace F, a subspace A of F2 to the N, okay, of some dimension. So here we take the dimension to be lambda by 2. Okay, lambda is the security parameter. And the second thing you need are two vectors, SS prime in F2 N, okay? And then we call this the coset state. So A SS prime, this is defined as follows. So it's minus 1 to the, what is it, sum over A in capital A dot S prime and A plus S, something like that. Okay, let's check quickly. Where did I keep it? Okay, so this was the, yeah, okay, so I missed the normalization factor. So let's fix that. 1 by square root size of A. Okay, so that's the definition of the coset state. And why we introduced this was because we were looking at so remember that, you know, we were looking at this game. So the construction, so the scheme that we were looking at, right, the rough template was the following, right? So we had gen 1 to the lambda. So this is the, this was roughly the idea, right? So this would return, yeah, I don't want to do the whole thing again. Yeah, okay, so the scheme that we're going to use now, I'm just going to tell you this and then I'll quickly remind you. He wasn't there in the previous lecture, so I'm just quickly recalling what we did. Okay, so we return a random subspace, so you return A of size lambda by 2 from F2 to the lambda, okay, and then encrypt H. So you're given the, you know, this is the secret key A, right, and M, and what you do is you sample SS prime from F2 to the lambda, and then you output the coset state ASS prime. So this is the state that you output, okay, together with M XORed with H acting on SS prime, okay. So yeah, let me finish writing the scheme, then I'll quickly say a word or two about how we defined it. Okay, so given the coset state and some output string C and the description of the subspace S, yes, it's a subspace, sorry, you're going to get So there's a way to recover SS prime from the coset state ASS prime and the description of A. Okay, and then using this you output C XORed with H acting on SS prime. Okay, so this is basically instantiating this idea that we had from this scheme by Broadbent and Lord, which was that so in that scheme what we were doing was, let me write it with another color quickly. So what we were doing was, so gen would return a theta. Okay, so this was 0 1 lambda. So instead of A, it was returning a theta, and then encrypt would take theta as an input. Okay, it would take the message, and it would do the following. So instead of sampling SS, you sample some x from 0 1 lambda. Okay, and you do this. You do M XORed with x. Okay, so you got some encoding x. So you did this. Actually, yeah, let's add a random oracle, right? Because remember that if you just XOR with x, then you can anyway guess half the x, right? You can measure the okay, let me write the scheme first. Okay, so instead of ASS, you had h to the theta x. Okay, so if I give you the state, right, and you just randomly measure it, at least on half the basis, you will get the correct basis, right? You will measure in the correct basis, and so you will learn x on those bases. So if you had M XORed with x, then at least you would learn some bits of the message. Okay, so it's obviously not secure. So therefore you need, so that's why they introduced this random oracle, that not only do you need, it doesn't suffice to know some x, intuitively you need to know all the x's so that you get the correct evaluation of the random oracle. H is the random oracle. Okay, maybe I should mention that. So H, so this H is the random oracle. Okay. So now the issue was that this scheme, we do not know the security. We do not know whether this scheme is secure or not, and so therefore to get around that problem, these people substituted this. So these are the Wiesner states or the BB84 states. So they substituted these states for coset states. Okay. So instead of using this and theta, we are going to use A instead of, so A basically plays the role of theta, and instead of x we have S and S prime. Okay, so that's the intuition. I'm just reminding them what had happened last time because one of us wasn't here last time. Okay, so this is the definition of the coset state, and we were now looking at how the proof technique works. Okay, so one thing that we mentioned last time was that it's a very similar monogamy of entanglement game that we had for. Okay, so the property that we needed, so property of coset states that we need is a monogamy of entanglement. Okay, and this is sort of a strengthened version. So monogamy of entanglement. So it's actually a strengthening. So MOE. So strengthening. How is it strengthened? So it's strengthened in many ways, but one of the key things they do is they allow membership oracles. Membership oracles. Access. Okay, so you can access. So there's an oracle that tells you whether you belong to the space P A plus S and P A perp plus S prime. Okay, so all the adversaries get access to this as well. So monogamy of entanglement game, I suppose you would remember, was something like this, right? That you're given A, you're given the state, you're given the state intuitively, right? And then it had to partition the state into B and C, and they then get some secret information. So say the basis or some secret key, right? Or in general, it's some secret key. Or let's just call it a basis. Like, so you get extra information, and then you have to state encoding, say x. Okay, and then you have to output. They both have to output x, xp, xc. So the game was something like this: that if you do not have access to the basis information, you have to output it. This you couldn't do. And the point was now that even if the basis is given to you at this later point, and now the additional thing we are doing is that we are giving you access to an oracle. So intuitively we are giving access to an oracle that oracle say p sub x. Okay, so you can query the oracle at any point you want, and it will say yes when you query it at x, and it will say no otherwise. Okay, so we saw that for BB84, such a scheme is like you can break the monogamy of entanglement game if you have access to such an oracle. Okay, while for coset states that is not the case. Even if you give it access to these membership checking oracles, it does not break the monogamy of entanglement game. That was kind of the crucial thing. So this is sort of the review of what we had discussed last time. Okay. Okay. So now we'll see why we're talking about these oracles and so on, at least at a high level. So let's do that. So now we're trying to base security on reprogramming games. Okay. So this we had actually written last time, so let me quickly write it again. So H was a random oracle from f to lambda cross f to lambda to 0, 1. Okay, then we said A, B, C have access to P A plus S and P A plus S prime, A perp plus S prime. Okay, then H S S prime goes to perp. So this is the same as H, except H of S S prime is replaced with perp. Okay, and then we had H0 was the same as the random oracle, and H1 was the same as the random oracle except that you XOR with 1. Okay, so H at all inputs accepts SS prime, and then at SS prime you simply XOR with 1. Okay, and then so this I think we had done last time, and now I'm going to add the new step. So there's something called challenge modes. So there are 2 challenge modes in this game. So one is the identical challenge mode. Okay, it will become clear in just a second what is going on. So identical is that B sub B is the same as B sub C is the same as B. I'll tell you what these variables are in a second. And B is sampled uniformly at random. Okay, and then the independent mode is, so this was identical, so BB and BC are identical. Independent is you sample them independently, BB and BC. Independent mode is BB is sampled from 0, 1, and BC is also sampled from 0, 1. Okay. So what is the game here?
What's the meaning of challenge mode?
It's just a word. So basically it's the way the verifier is going to challenge, the challenger is going to play. So basically they're combining 2 games into one, and they're just saying that depending on the way the challenger behaves, we'll call them 2 different games.
And also I asked before, so how do I define A perp?
Oh yeah, this I'll give you a formal definition. I was reading up on coset states. There are things that we'll look at later, but A perp is defined as follows. So it's the set of A's such that, so set of A primes such that A prime dot A is 0 mod 2 for all A in capital A. It's almost like a dual. So basically you take any vector in the big subspace in capital A, the dot product with A prime has to be 0 modulo 2 because we're in F2. That's the definition. Yeah, thank you for reminding me. Okay, although this level of detail is not really needed, but we will go into the actual detail in a little bit. Okay, so what does the game do? The game starts with, as usual, challenger. Okay, so samples a coset state. So let's start. Samples a coset state. A SS prime. Okay, and sends the following. So what does it send? So it sends the coset state itself and a random oracle evaluation of at the point SS prime. Okay. So A gets access to H of SS prime going to perp. Okay. So remember, this is the same as H, except that SS prime becomes perp. And then A sends, bipartite state as before to B and C.
What does it mean by samples a coset state?
Something like this, that you sample A as a subspace uniform, and then you sample SS prime, and then you create this state. Yeah, I haven't proved that you can create this state. Like there's lots of small things I haven't proved, but this is a relatively high level idea. So you do that procedure over there. So you'll be able to produce this coset state and the evaluation of the random oracle on H's. You send it, and then you have B and C, and then you send the description of A. Okay. So remember that A is overloaded. So A is not a register here. So let me just write description so you don't get confused. Okay. So A is the subspace. Okay, and then B and C are the registers that are sent to B and C. And then you output B prime and B double prime. Wait, what did I do? Did I mess up? Give me a second. No, it's fine. Okay. And as before, you win if B prime equals BB and B double prime equals BC. That's a bit weird. Okay, give me a second. I think I messed up a few things. So H B sub capital B, H B sub capital C. Okay. So H0 and H1 are defined here, right? So H0 was the original oracle, the original random oracle. H1 is the original random oracle, except that it flips the bit at SS prime. Okay. So A gets the same as the original random oracle, except that SS prime is replaced with perp. So that's the random oracle this A gets. B and C get a slightly different random oracle. So they get, depending on the value of B sub B. Okay. So this would depend on the challenge mode that I was saying here. Okay, so B sub B and B sub C are random variables. Basically, they're random bits, and we can either choose them to be identical or choose them to be different. And we'll show that how these two cases are related. The analysis would depend on this. And the job of B and C is to figure out which random oracle is given to them, whether they were given the unmodified random oracle or the one where the evaluation at SS prime was XORed with 1. Yeah, sorry, what was your question?
What is 1 plus 12, for example? So if I call H1 at SS prime, so if I will give 1 plus 12 by the answer, so will it be 12?
Why will you give H is the standard random oracle, right?
So when I am having access to H1 and I am querying at SS prime,
yeah,
then I will be having 1 plus HS S prime.
This is what outputs. So H can never output perp, right? H is the original random oracle.
Oh, HS S prime will also not output perp.
Yeah, H is the original random oracle. So H cannot output perp. H sub SS prime going to perp can output perp exactly at that point. H0 and H1 So H0 is the same as H, and H1 is the same as H, except that it flips the bit at SS prime.
I was confused. There is subscript or so SS prime going to perp is different oracle than.
Yeah.
Sorry.
Yeah. These are just. So it might be slightly confusing, but that's just notation. So there's nothing very deep happening. Is the notation clear? What is happening? Okay, so this is the game they consider. Why this game and all the details we'll cover in the coming lectures, but at least the definition is should be clear at this point. Okay. Okay, so now let's see what they're saying about this game.
So what is the different mode? We got BB equal to BC equal to B, like good winning condition. What is this other condition that they randomly match their answer?
What is this other condition that they randomly match their answer?
So here the win condition doesn't require that BB equal to BC, right?
Yeah, you just have to guess which one was given. In one case, I will give both of you the same random oracle. In the other case, I'll independently sample whether I give you H0 or H1. And in both cases, the objective is to guess which was given to you. Right? That's what the game is saying, right? That they have to output which one was given to them. Okay? Okay, so let's see. Okay, so in this game, in the identical challenge mode, right? B and C try to distinguish between H0 and H1, that is whether the random oracle was programmed or not. Because if even one of them sees that it was programmed, then they know that they both got the same thing. Okay. 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 So now, this is a claim, which is that by a sequence of standard variable substitutions, unclonable indistinguishability of this scheme can be based on the identical challenge mode. Of this game. Okay, that's a claim, so we'll take it at its face value.
What is the point between giving the random oracle to
So everyone should have access to the random oracle, right? That's that's just the standard methodology. So you always start from there, and then you can argue that even if you make small changes, it's indistinguishable. So by default, you give access, give everyone access to the random oracle.
So A just sends some information about the cosine state to the answer.
No, I think you're right. I think no, I think you're right, because A does not have. So the point is that A does not know SS prime explicitly, right? So in hybrid 0, like in the actual thing, A, B, C will all have access to the random oracle. Here, what they're going to show is that even if you replace A with having full access to the random oracle, you replace it with this restricted access, because basically you changed the value at one point, so you reprogrammed it. This should not make any difference to the winning probability. So this they're going to argue at some point. And why they're giving the value of SS prime explicitly, I think it would probably be related to the fact that you have to XOR the message with HSS prime, and normally you're given the encrypted state, right, as the output. So it's just giving the the unclonable state plus the. So if you cannot predict this bit, I think then you can show security. That's kind of the idea, is then you can XOR it. So I give you the encryption and the unclonable state, and you shouldn't be able to split it and send it. And so it's going to be related. Yeah. It's a little bit involved, but okay. Okay. So would be nice if they had more boards, like ones that could move. You could keep at least something written. Okay. All right. So that was the second point. Okay. What's the third point? So the third point is what Shreyas, right? Yeah. So the third point is related to what Shreyas was saying. So note that in the reprogramming game, right? So in the game, I'm being slightly lazy with the writing. Okay. So A has no access to the value of H at SS prime. Okay, that is very strange. You are explicitly giving it the value. Did I mess up? What did I mess up? I suppose it's just saying that the random oracle that you're giving does not give you the evaluation. So the input may be something else, and like it has no way of actually checking whether you gave it the correct value at the random oracle or you gave it some other value.
But HSS prime is given to it.
Yeah, so that's what I'm saying, that from the oracle I don't think it can check whether this is correct or not, because it's not given the full oracle. That's
So
that.
know that it's being given HSS prime.
Yeah, so I think I have also not read the full proof yet, so I guess it will become clear. But at this point, I think they're just trying to emphasize that from the random oracle, it cannot learn the SS prime value. Maybe from the input it can, but because if it got some other input, it would not be able to distinguish. So then you can argue that it really doesn't know the value, something like this. I guess, I don't know. I will see. We'll see.
But we can distinguish the symbol curve or not.
Yeah, of course.
So then he can, if he queries on many inputs and gets some perp answer, then he will know that.
Yeah, exactly. But it's like the search problem, right? Like it's unstructured search, so it's going to happen with exponentially small probability. Yeah. Okay, so it doesn't know the value of SS prime. Okay, and this is different from monogamy entanglement or unclonable indistinguishability games.
This also assumes that this is computationally bounded channel.
Yeah. So the number of queries you're making is polynomial. We discussed this, I think, last time. Shreyas had pointed out, or probably it was Shravan or Ariman. I don't know. One of you two had. Yeah, I want to actually just double check. Give me a second. I will double check that the statement that I'm making is correct. Yeah, no, it does send this HSS prime according to the paper. So we'll see what they really mean later. Okay. Yep, they show one can assume A never queries at SS prime. Okay. Okay, so so I guess the main point is that whether I give you the full oracle or I give you an oracle where I've replaced SS prime with perp, this step is relatively easy to show, okay, compared to the rest of it. The fact that it makes no difference to your success probability. Okay, and then security of the identical challenge mode. Can be reduced to the security of independent challenge mode. Okay, so whether you sample these B sub C and B sub B independently or together, one can show that this is this does not change your success probability, and this somehow follows from careful analysis of Jordan's lemma. So Jordan's lemma we'll look at probably today or next time, we'll see. Okay. Okay, so this we'll do in a moment. And here what we're going to do is, okay, so here we focus on the independent challenge mode. Okay. Okay, this is just to have some high level idea of what's happening. Okay, so here's an informal claim. So there exists an efficient procedure that operates locally on both the entangled adversaries and outputs B prime P sub B and C prime P sub C such that B prime and C prime, so so the first property that they're able to show is that they're unentangled. Okay, so obviously this by itself is completely trivial. So the important thing is that the success probability of B prime, right, on guessing whether guessing H0 or H1, right, is PB. Okay, and similarly that of C prime is PC. Okay, And finally, the expectation PB times PC equals BC's success probability in the independent challenge mode. Okay, so the point is that when you're running the game in the identical challenge mode, right? So this is what is meant by distinguishing between H0 H1, right? Because both get either H0 or H1. So they're saying that when you're in this mode, in the first mode, then the success probability of B prime and C prime are essentially the same. Okay. But when you're in the independent challenge mode, then the success, the product is unchanged. Okay. So in one case individually you can match the values, in the other case the product is what matches, and that's what the winning condition cares about, right? It cares about the product. Okay, good. And this step was, remember the problem with Broadbent and Lloyd, right? Because for them, they could analyze it for unentangled adversaries, but they couldn't analyze it for entangled adversaries. And here they are proving that even if you start with entangled adversaries, you can construct unentangled adversaries with essentially the same thing. Okay, so I guess that must be simplifying the analysis a bit. Okay. So now let's look at some remarks. Okay, so to estimate pb.pc, right, we want to run b prime and c prime. Okay, but to run b prime and c prime, we have to give access to H0 and H1, right? Which is in the independent challenge mode. Okay. And A only gets access to H SS prime perp. Okay, so I guess they're trying to show that when you're trying to argue about these oracles, right, the guarantees hold when the oracle has been modified in some way, but the point is that when you try to create the reduction, you do not know SS prime in advance. Right, that's the whole point. That's difficult to do. So somehow they have to find a way of programming these oracles themselves. Okay, and this is where the oracle access to these guys will come in. That's the main thing. Okay. Okay, so now for this procedure to be useful, for this procedure to help with breaking monogamy of entanglement games. The procedure cannot know it. Okay. But, and because we're using coset states, it knows A and can access PA plus S and PA perp plus S prime. Okay. So now we're going to look at how, starting from A, P, and these oracles, how one can construct, given access to this oracle, how do you construct H0 and H1? So starting from this, how do you construct H0, H1 by only using these projections? So that's what we're going to do now. Yeah, I don't know how they think of all of this, man. It's insane. Okay, so here's the example. So, so H1, so H1 can be reprogrammed as follows. Reprogrammed as, right, so H1 ZZ prime equals negation of H okay, let me write down, it's slightly long, okay, so let me write down the definition, then we'll try to understand what's happening. QSZ equals 1 and QS prime Z prime equals 1. This is otherwise SS prime goes to perp and you ask on ZZ prime, where QS on Z is a delta function outputs 1 only on Z equals S, 0 else. Let's just say this. Okay, so yeah, you could also just write delta SZ, I think, or delta sub S, whatever, doesn't matter. Okay, so suppose you had access to such a function, right, that gave you 1 when it matched S and gave you 0 otherwise. Then you were sort of done, right? Because you just run the, so you don't know the value of S in advance, right? You're given some input, you check whether it matches S or not. If it matches S and S prime, then you do whatever you have to do, right? Otherwise, you let it do. Right? So this is relatively straightforward.
So how is it different from the definition?
You're trying to use this. You're only using this oracle to. But yeah, you're right. It has access to H. So that's, we wanted to do it without access to H. Well, yeah, I think the point in the end would likely be that to do independent sampling, you're basically replacing this value with a random bit, right? Essentially, because so if I XOR H of SS prime, right, with a say random bit, or I just substitute it with a random bit, right? Let's do the following. Okay. So if I substitute at SS prime, so let's call H prime SS prime, this is just a random bit B, right? So with half probability this will become H0, with half probability it would become H1, right? So I think this is the direction in which they're going, that even if you don't know H, as long as you can detect that you queried at ZZ prime matching SS prime and you can do something else, that should sort of be enough, I'm guessing. But that is a good point what you raised, because I started off by saying that I want a construction that only uses H with SS prime substituted with perp, which hasn't happened there. So that is a good point. But let's see how they proceed. Okay. So all of this was assuming that we have such an oracle, right, that could tell you whether you queried at S or S prime. But you can check actually. So here's how. So here's how to construct QS of Z. So how does it work? So one, you check if Z is in A plus S. Okay. There are classical algorithms for a lot of these things. I'm also not very familiar with them, but a lot of these steps you can do. So one of the steps you can do is you can check whether a vector belongs to A plus S. If I give you the classical description of A and the classical description of S, you can check whether it's in the span. Yeah, I guess you could just do Gram-Schmidt, right? Like you could, not even Gram-Schmidt, you could just take inner products and you can see what components you get and if the normalization works. So you can think about it. Because this is poly-sized, remember this is something we discussed last time as well. Okay, and then you can check whether it's lexicographically ordered. Is Z lexicographically the smallest? Okay, so these are steps you can do classically, which I'm not going to prove. Okay, so how does that help? So okay, I think I misspoke. The point is we don't have access to S, right? That's the whole problem. So even we just have a classical description of A, right? We don't have access to S. So even though you can do it probably classically if you had the description of S, you don't have the description of S. But you do have access to the membership oracle, right? So you can just run the membership oracle, it will tell you whether or not it belongs to the thing. And apparently step 2 can be done by essentially enumerating. So you enumerate each coordinate. Each coordinate into Gaussian elimination. To see if there exists Z prime that's lexicographically smaller than Z. Okay, so you list all the vectors in the lexicographical order, and then you check that whether Z minus Z star is in the span of A.
Isn't the lexicographically smallest element in A plus S, S and Z?
It should be lexicographically smallest should be S, but then you'll probably learn S. Yeah, but that's fine, I think. I think that's the whole point, that if you actually query, if somebody gives you the smallest element, lexicographically smallest element, you can check it's the lexicographically smallest element. Doesn't mean you can find it yourself.
So that is basically like a membership oracle to tell whether it's S or
That's what you're fully. This is what Q was, right? This is what we were constructing. Yeah, that's exactly what we are constructing. So we don't have a membership oracle directly for S. We had it for the cosets, but from the cosets you can actually construct for S as well.
But isn't that solely enough to construct QS? Like just point.
Isn't that being what QS?
Yeah.
Oh, you're constructing QS from. Wait, which point two? I think I wrote 2 point 2s. Let's call these A's and B's. You meant B2? A2. Okay. Is lexicographically. Yeah. So I'm basically telling you how to construct them. Yeah. So this 1 does 1, 2 does 2. Yeah. What was your question again?
Like, what is the necessity of A1?
Because before you start checking whether it's the smallest element, you want to make sure that it's in the set, right? Because like the 0 vector could be the smallest vector, but you need to make sure that it's actually in the coset, right? Yeah, it's not doing anything deep. Yeah, you're just basically it's just a membership oracle for S, and we're constructing it from the membership oracles of A plus S.
A1 just seems redundant if A2 is there.
Yeah, sure. It's just giving you intuition. Like this is the first thing you want to do is you want to make sure it actually is in the set, and then you want it to be the smallest. Yeah, sure. Okay, good. Okay. So this was the example that you can actually, even though you don't know SS prime, just from the membership oracles, you can reprogram an oracle at that location. Okay. And it's unclear how you would do it without the membership checking oracles. So that's one of the issues with the Wiesner state construction, at least for using such an approach. Okay. Okay. So now we try to prove security in the independent challenge mode. Okay, so that's what we're going to do now, informally, of course. Okay, so how does it work? So suppose that an adversary ABC, okay, has non-trivial success probability half plus gamma for some large gamma, right? Okay. Then the procedure that we mentioned, right, for so we convert BC even if they're entangled into something that's unentangled, and we are able to reprogram the oracle using these ideas. So using the procedure above, one can output PB one can show that PB times PC is greater than half plus gamma by 2 with non-negligible probability. Okay, because we argued that yeah, I'm actually not sure why we need the procedure here. Because PB, PC we just defined to be the success probability of B and C, right? So obviously the product will give you the full success probability just from here. I'm missing something. What am I missing? Give me a second. I see. So yes, I think they are. Okay. Give me a second, you guys. I think I messed up something because I see. Okay, so I think I'll just, there's some part of the argument which I will clarify next time. I think I'm getting a little bit lost, but the argument that we had before somehow shows that if you start with any adversary for the independent challenge mode, then one can construct, one can deduce using that procedure that the product of the success probabilities has to be half plus non-negligible, okay, simultaneously. So basically it's saying that at least one of them, so the high level idea is that at least one of them has to be querying the random oracle at SS prime. That's the whole, the bottom line. Because you want both the success probabilities, the product to be greater than half plus negligible, right? So it has to be that at least one of them has queried at the random oracle at SS prime. So that's kind of what they're trying to formalize. I was thinking that way, but yeah, I have to. It's not very clearly written. I'll think about it more carefully. But that is supposed to be the idea, that you start with an entangled adversary, you replace it with unentangled adversaries that are two different.
But you still ensure that it wins with probability greater than half.
Yeah, there are two separate ones. Where the entanglement is used, I'm not sure, because even in the monogamy of entanglement game, you could have used entangled adversaries. So I'm not really sure where that step is being used. So, but we'll do the full formal proof, don't worry. Like once we do the full formal proof, I think this intuition will become clear. But this is just a sketch, okay? So now, so what one can do is, oh, I think I see now, okay. So the next step says the following, okay? So now you're in the unentangled setting, okay? So in the unentangled setting, if B prime never queries H0 or H1 at SS prime, okay, the best probability of guessing which you were given, right, of guessing which among H0, H1 was given is at most half. Correct? So if B prime, so now here's the crucial bit, right? B prime is not entangled. So if you just look at B prime by itself, if it does not query H or H0 at SS prime, the probability of distinguishing these two is at most half, right? This is just trivial. Huh?
What was B prime?
Oh, B, so you started with ABC, and that's the thing we did. I should write. So you convert ABC into, so that's an adversary where B and C could be entangled, which wins with some probability. You can convert that, that's a claim, into another adversary which you call B prime and C prime, such that B prime and C prime are no longer entangled. And then we made some guarantees about the success probability as well of B prime and C prime. So in particular, we argued that the product of the winning probabilities for B prime and C prime would still be what was, I can tell you the exact statement. The product of the winning probabilities, you can see it, right? Yeah, so the product of the individual probabilities of guessing whether you were given H0 or H1 is the same as the success probability of the original adversary in the winning game. Okay, yeah, so that's kind of what I was messing up. Okay, so if the original adversary is winning with this probability, then the product where this is the winning probabilities of B prime and C prime, the product has to be at least this, and so the best probability of, so now the important thing is it's a product, right? So I think what I said earlier was also a little bit wrong. So both of them have to have measured at the same time, otherwise you'll, okay. So this is at most half, but because the product has to be greater than half, therefore you have to have measured with non-negligible. You have to have queried. Okay. Okay. So since this is the case, so thus it must, and you know we have this statement is true, right? So to satisfy star, it must query at SS prime. Okay, and this can be extracted. So not just query, but query with like enough weight, right? Because it has to do it with non-negligible probability. So, and can be extracted by measuring the query register at random with non-negligible probability. Measuring query register. Okay, at this point I'm just scribbling things. Okay. I'll read it. Okay, so thus it must be querying at SS prime, and this can be extracted by measuring the query register with non-negligible probability. Okay. And so you can repeat the same argument for C prime, and what that would do is it would actually allow you to extract SS prime. Okay. So it would allow you to extract SS prime for both B and C locally, right? Because we argued that the product has to be greater than the winning probability of the original game. Okay, this is just a high-level thing. I'm sorry I got confused. I wrote it like weeks ago, and then now I was getting a little bit lost. Okay, so let me just write it here. So one can repeat this argument. Oh shit, is it just till 5? So we have like 20 minutes, 15, 20 minutes? Oh. Yeah, I'm so sorry. I think today I wasted.
Students or like people who don't want to do the proof, or
No, it's for understanding the proof, because if I just directly start telling you the proof, you'll get lost in the details. So at least this way you have some outline of, that we'll start with, this is the game we're considering. It has 2 different modes. One mode is related more directly to the game that we want to look at. The second mode is allowing the analysis to be easier. How you're using the, the membership oracles to reprogram the random oracle. How you're getting rid of entanglement at the intermediate step. How that is related to the success probability of the original game, and then because the product is greater than half, you're able to extract S and S prime, and thereby breaking the monogamy or entanglement of the coset state game. So this basically gives you a high-level idea of what's happening, and then once we go into the details, everything will become crystal clear. Because yeah. But if you try to go directly, you'll get lost for sure. You're like, what are you doing? Why are you doing what you're doing? It'll make no sense. So it's I think the way to think about it is to read the high-level thing, do the actual proof, and then read the high-level thing again.
yeah,
Then it'll make sense. But we can't do that in class, so okay. And one can do similarly the same thing, right? Similarly for C prime, one can do this, okay? And then, like I was saying, but this violates the monogamy of entanglement. Okay, and so that's a contradiction, because there's a separate proof that you cannot win the monogamy of entanglement game. Okay, so this will complete the proof sketch. Okay, I'm sorry. I wish I had it a bit more internalized so I could tell you things. Okay. But so far we've only done the analysis assuming that we're in the independent challenge mode. Now we'll try to understand how the independent challenge mode is related to the identical challenge mode. Okay. So relating identical challenge mode. to independent challenge mode. Okay. Okay, so we first consider the independent challenge mode. And then give a nice characterization of the state produced by Alice. Okay, so suppose A SS prime and the oracle H of SS prime going to perp are chosen randomly. Okay. Oh, should I remove this? Maybe not. Yeah, let's just keep this. Okay, so these are chosen randomly. And then we let sigma BC denote the joint state shared by Bob and Charlie. After Alice's stage. Alice's stage meaning, after Alice has done the output. So we are assuming that the state here is sigma BC, right here. Okay. Here's a definition. So pi little b and pi little b c, so capital C, for little b in 0, 1 are as follows. Are defined as, so pi 0 capital B says what? So this says run Bob on its own part. So run Bob on its own part, sigma B of sigma, with oracle access to 80. Okay. So this part we are calling it, so call it U. Okay. Then we project onto Bob, outputting 0. Okay, so we are projecting on this 0, 0, and rewind. Okay, call it U dagger. Okay, so the entire procedure is this: U dagger. So you apply U, you apply the projector, and then you apply the dagger. Okay. So that's what pi 0b is, okay? And pi 0c is the same, oh sorry, pi 1b is the same as pi b0, except oracle access to h1 and project on 1.
What is
Yeah, so the basically Bob's part is this part.
U is unitary, right?
Yeah, it's a unitary.
So how did it do it?
It's just what Bob does. It's the adversary B, right? The adversary B is applying some operation. So you run the operation. You
Apply some randomly or what is
no, whatever Bob does. You're given ABC. You're given the adversary, right? So you're defining these projectors given the adversary. So yeah, I didn't write it properly. So yeah, so these projectors depend on the description of the adversary. Okay.
Where is U defined? How do I understand that?
No, you're given an adversary.
So he's doing something and you are calling it U.
That's it. No, nothing very deep.
What exactly does rewind do?
U dagger.
But that isn't actually rewinding, right? Because there is a projection in between.
Yeah. So that's why you're rewinding when you just run it backwards, assuming you got that outcome. It wouldn't always work. Yeah. There's like lots of subtleties there. Yeah.
This is like he is measuring in some basis.
You can also think it's measuring in the zero in that basis. Yeah. That's why I wrote it explicitly, because otherwise it gets a bit confusing. Okay. Yeah, this is a crazy paper. We learn a lot by the end of it, but.
Maybe he'll kill the crypto enthusiasm for some.
That's okay. I mean, this is the game, right? Well, not this particular game, but okay. So pi 0c and pi 1c are similarly defined. For Charlie instead. Okay, so that's fine. And now. So this is the projector for Bob's success on HP, and pi BC is the projector for Charlie's success, right?
pi 0c and pi 1c will also include U only?
No, then it'll be for Charlie, right?
But the
So
same unit
run
or different
Charlie.
unit, right?
Ooh, Bob and Charlie are different adversaries, right? So you run whatever Charlie would
Sure,
run.
but on two different hill vertices they can have same unit, right?
Yeah, but it's arbitrary. They can do whatever they want on their space, right?
No, they are not communicating, so if I have measurement in the same basis, that doesn't sound
No, they are different registers, right? This is acting on Hilbert space C. This is acting on.
This thing will be orthogonal, I'm not saying that. I'm just saying that are they performing measurement in the same basis, both of them?
They may not. Well, how does it matter? I don't think I'm understanding the source of your questions.
Yeah, I'm just thinking that there is this measurement U dagger get 0 bra 0 U.
Yeah, this is on register B, right?
Yes, sure. And
So the other one would be like 0, 0, like on CC, whatever. And then say V dagger.
yes, it's V dagger, something else. Could be same, could not be the
Yeah, there's no constraint. Yeah, exactly. Yeah, it's because we're considering the most general adversary, so we don't want to make any assumptions, right? So B and C have to be arbitrary. Okay, so this is good, and then by definition, the success probability in the independent challenge mode is the following, right? So it's pi 0b plus pi 1b by 2 tensor pi c0 plus pi c1 by 2 trace sigma sigma, right? This is fine, right? I mean, this is just by definition. Because with probability 1 half, you give access to H0 independently, right? And with probability 1 half, you give access to the other one. And so it's a little bit strange because these projectors are containing, like internally, they have the fact that you're using one oracle or the other. So it's kind of baked into the projector. Okay, so this is number 1.
So pi 0b and pi 1b, they are not still complete. In the sense that pi 0b plus pi 1b is not identical.
No, because they're using different projectors. Yeah. Yeah, that's a good observation. The notation is misleading a little bit in that sense. Yeah. All right, and then we have some notation. Let phi sub p belonging to a real number denote the eigenvectors pi 0b plus pi 1b by 2 with eigenvalues p and 0, 1. Okay, and so for simplicity, assume that the eigenvalues are all distinct. Yeah. Oh, that's what you were asking. Pi 0 plus pi 1 is not identity. Yeah. True.
But this is still, so it's not a projector because of 2.
It's not a projector because of half. Oh. Yeah, it's like a POVM, right? Like with some probability you're making so much more.
Tell the other element.
Yeah, it's a POVM element. Like you can always define identity minus the rest with the other part for it.
That is distance. So they want to find maximum success probability and they are not considering the full space. So I mean they have some knowledge or something because they are considering like 2 elements.
Yeah, there's like the random oracle sitting in all of this. So it's not that you just
if
have.
I want to distinguish 2 objects, I would ideally like 2 elements in the POV.
Mhm. Yeah, but you have oracle access to something, right? So it's not. So if you just have a state and you want to distinguish, you have some, then it sort of makes sense. Here you have this fact that you have oracle access, so it's not just the same optimization problem. It's a slightly different optimization. Okay, so this is fine, and then we let psi p. Oh, sorry, psi q. Wait, what was phi q? Oh, these are the eigenvectors. Okay, and so you have.
But still, so pi 0b plus pi 1b is a projector, right?
Just a sec. Let me finish this and I'll get to you. C. Okay, so it's the same thing except that you're doing it for the C projectors. Yeah. Sorry, what was the question?
If I forget about the 2, I divide by 2, then pi 0b plus pi 1b is projector, right? Here they are orthogonal.
They're orthogonal. Why are they orthogonal?
Because you apply unitary onto orthogonal state, they remain orthogonal.
No, it's not the same unitary, right? Because you're given. Wait, is it the same unitary? Give me a second. No, with pi 1 you're given access to h1, right? This is what I was saying, right?
But this is not clear where they are using it even in this expression, because I thought that
This is something I wrote just to convey what the rewind procedure meant. That's why I put the u. Like if you want to explicitly write it, you can write it as depending on h. 80.
yes, sorry, so they are different.
Yeah. They're not the same. Sorry, the notation may be a little bit
My
misleading.
other question is also not valid. They are different things.
Yeah. Okay. Okay. Shoot, we just passed time. Okay, let me write the last note and then we're done. Yeah, so one can write sigma as sum over pq, alpha pq, phi p psi q. Okay, we'll do the rest later. Yeah, I'm sorry, it's going to get more involved in the coming days. Yeah, sorry, I got a bit confused today, though. That was not very helpful. Okay, thank you. Oh, yeah, I have not.
Did you not upload the question paper?
You were supposed to upload it?
Yeah.
Oh, I thought it's like 2 days before the. Mine is on Saturdays this time. Or Friday, something like that.
Yeah, you have time.
Yeah. Is it coming in the? I don't know. It's in this part. I don't think we have anything technical here. I think the parts where we've done proofs, I think is fine. Let's not worry about the. Yeah. These things will probably not make as much
It's
sense.
difficult to make questions for exam in a course like this.
Yeah. Tell me about it.
Everything is different, so it's difficult to ask.
Yeah. Anyway, the feedback. Thank you. This is the one for last time in case you didn't fill it.